In this video we are going to have a look at how a quantum process and HOLON approach to reality explains the stability of matter, why some elements are stable and others are not. We will also find a clue to explain why the universe is apparently expanding. We saw this diagram earlier in the series. We were looking at the positions of quantum charge pairs on a line conductor at random times in their oscillations. We saw how they formed a quasi-stationary charge distribution. Although this distribution looks complex, it has a relatively simple mathematical structure. If you start from the center of the HOLON, you add up all the quantum processes to say 1/5 of the way to the outer boundary of the HOLON, and plot that number on a graph, and then count up all the quantum processes between the center and 2/5 of the way to the outside, and plot it on the graph, and then do the same for 3, 4, and 5/5, then you generate this relationship. The blue line is the best fit to the data. The formula of this line is remarkably close to the very simple square power relationship indicated by the brown line, and there are reasons to suppose that this is not a coincidence. This power relationship holds for nearly all orders of magnitude, any HOLON size, except for extremely tiny HOLONs that we will come to in a minute. This graph shows that HOLONs are fractals. Line HOLONs of all sizes have this internal quantum process structure, and because of symmetry, this structure applies to cross sections through two-dimensional disks and three-dimensional spheres. Now, as part of the calculations to find out these positions, it was necessary to calculate the speeds of those quantum electrons, and the speeds of these pairs for a HOLON cross-section 20 meters long is shown in the next diagram. The speeds of 2000 quantum electrons of 1000 quantum process pairs are shown in quantum meters per quantum second. These units remind us that we are looking at speeds of quantum electrons that are a part of interfunctional quantum processes, whereby no component can exist without all the other parts of that quantum process. So distance, one-dimensional space, cannot exist without time, and time cannot exist without distance. In this particular example, the speed of the sampled quantum electrons is extremely low, less than 1000 quantum meters per quantum second, when compared to the speed of light, which is 300 million meters per second. But what happens to the speeds of quantum electrons as HOLONs become smaller and smaller? We are interested in the region right near the origin of our graph, indicated by the red arrow. Some really tiny HOLONs with extensions between 1 × 10⁻⁻10 and 1 × 10⁻17 meters in length were looked at. The method used to produce these results needed to use an iterative mathematical method that is very taxing on computer processing power. And the smaller the HOLON being investigated, the more processing power was needed to produce results in a reasonable time. So the results here are based on 200 quantum electrons of 100 quantum process pairs for each HOLON. Even with this small number of quantum electrons, the calculations took a full day of processing for each size of HOLON. Nevertheless, the results are very interesting. The left-hand column shows the size of the HOLONs investigated. The largest at the top of the column is 2 × 10⁻10 meters in diameter. That is just 0.902 of a meter and the smallest at the bottom of the column is 1 times 10 to the minus 17 meters, which is a staggeringly small 0.1601 of a meter in length. The second column shows that as the extensions of the holons become smaller, then the quantum processes that give them their existence also have to become smaller. This means that the pairs of quantum electrons have to be closer and closer together. This in turn means that the mutual force of repulsion between the quantum electron pairs becomes ever larger. So the speeds of the oscillating quantum electrons increase. The third column shows the fraction of our 100 pairs of quantum electrons that calculate as having speeds faster than the speed of light. It was also the case that because of mathematical chaos, the positions of the quantum electrons exceeding the speed of light were found to be a very long way outside of the Holon boundaries. Let's have a closer look at the speed data. The left-hand graph shows the mean quantum speeds of the quantum electrons in different sized holons. As the holons become smaller, the speed of the quantum electrons becomes higher. A best fit equation shown on the graph can be found, linking the average speed of the quantum electrons to the holon diameter. And we see from this that a holon that is 1.51 times 10 to the minus 15 meters in diameter has quantum electrons with an average speed of the speed of light. But we can get a lot more information out of the graph on the right-hand side. It shows the fraction of the 100 quantum electron pairs in each holon that have speeds greater than the speed of light. Because of the huge range in cross-sectional distances, the holon diameters are shown on a log scale. As we come down the left-hand axis, the holon diameters become smaller. At the top, with relatively large diameters, there are no quantum electrons that exceed the speed of light. Then, when the diameter reaches 1 times 10 to the minus 14 meters, some of the quantum electrons have quantum speeds that exceed the speed of light. As the diameters become smaller and smaller, the fraction of quantum electrons exceeding the speed of light increases until we reach a diameter of about 1 times 10 to the minus 17 meters, where virtually all the sample quantum electrons exceed the speed of light. Now, if we were talking about quantum electrons being particles, then this graph would be meaningless, because no object can exceed the speed of light. But here we are talking about quantum electrons, which are not objects, but are inseparable parts of a quantum process. So how might we interpret this diagram? Well, if we draw a best straight line through the data that relates to the smallest 5 holons, this gives us the equation on the right-hand graph. From this, we can calculate the holon diameter where all the quantum electrons exceed the speed of light, and the diameter where no quantum electrons exceed the speed of light. This is the same diagram, showing the calculated limit in red and green. The holon diameters are shown on the right in meters. So what can this diagram tell us? Well, remembering that our holons are made from quantum processes, of which their quantum electrons are an integral part, we can suggest that the quantum electrons that have velocities that exceed the speed of light escape from the holon boundaries, taking their quantum processes with them. So holons with an extension greater than 1.63 times 10 to the minus 14 meters are stable, because they have many stable quantum processes that contribute to their structural boundaries. Holons with extensions between 1.63 times 10 to the minus 14 and 1.39 times 10 to the minus 17 lose some of their quantum holons, so their boundaries are unstable. And holons with extensions below 1.39 times 10 to the minus 17 meters do not exist because they have no quantum processes with which they can build boundaries that define their existence. So, above the green line, holons are stable. Below the red line, no holons exist. And between the two, we have holons that are unstable. So how good are these predictions? Can we see any evidence for this in the real world? Let's put some atom holons onto our diagram. The two blue circles represent the smallest atom holon, helium, and the largest atom holon, cesium. Clearly, they both fall well within the stable holon part of the diagram. It is easy to conclude that all holons bigger than atom holons will also be stable. So unsurprisingly, all the normal matter we see around us is stable. So what about the other regions in our diagram? Here we have placed on the diagram the smallest neutral holon whose diameter is reasonably accurately known. And this is the neutron with a diameter of 1.6 times 10 to the minus 15 meters. We see that this neutron holon, which is known to be unstable with a half-life of about 15 minutes, falls well within the predicted unstable holon region. And taking into account the vast range of possible diameters, it is just a hair's breadth away from the 1.51 times 10 to the minus 15 meter holon diameter that corresponds to an average quantum electron speed matching that of the speed of light. This relationship between the speed of light and the stability of the neutron is totally outside the scope of the prevailing particle and space view of reality. Yet this relationship emerges naturally from a quantum process and holon analysis. Perhaps this result is just a fortunate coincidence, but we can also place on the diagram a uranium nucleus, which is one of the very largest nuclei. And here we see this nucleus with a size of 1.5 times 10 to the minus 14 meters falls just inside the predicted unstable region, or perhaps more relevantly, just outside the predicted stable region. And indeed, it has a very long half-life of 4.5 times 10 to the 9th years, a fact that greatly supports the quantum process and holon paradigm prediction. We conclude that subatomic particles with diameters between 1.63 times 10 to the minus 14 meters and 1.51 times 10 to the minus 15 meters are potentially unstable. And indeed, many unstable nuclei have been discovered, some 2,400 with half-lives shorter than 60 minutes and 730 with half-lives greater than 60 minutes. Only about 253 nuclides are regarded as stable, and these are essentially the isotopes of the stable elements in the periodic table. There is, however, speculation that these too may also be unstable, but with lifetimes so long that their instability is unobserved. Now, although the quantum process and holon prediction of holon stability is good at predicting the stability and instability of atomic and nuclear-sized holons, there is an apparent anomaly that needs an explanation. The anomaly is the position of the proton holon in the stability diagram. Here we have added a proton holon to the diagram. It has a diameter of 1.7 times 10 to the minus 15 meters, and a hydrogen atom holon that has a diameter of 1.2 times 10 to the minus 10 meters. The anomaly is that the proton and the neutron have very similar sizes, 1.7 times 10 to the minus 15 meters and 1.6 times 10 to the minus 15 meters, respectively. So why, as far as we know, is the proton holon stable and the neutron holon unstable? We need to look at the products of neutron instability. In this diagram, we are showing how a neutron decays. In particle terms, the neutron on the left becomes a positively charged proton by emitting a negatively charged electron and an antineutrino, one of the family of super small neutrino particles that are almost impossible to detect. The green arrow shows how an electron and proton together form a hydrogen atom. Now this explanation, which undoubtedly fits experimental facts, is adequate as far as it goes, but begs some important questions. What, for instance, drives this decay? How come a neutral particle emits a positively charged particle and a negatively charged electron, even though these unlike charges should attract each other with a powerful electric force? And why is it so difficult or even impossible to observe the antineutrino particle that needs to take away the excess energy? Let's have a look at the quantum process and Holon explanation of this process and see if it does any better. Let's first note that it is not unreasonable to suppose that any holons with diameters between 1.51 times 10 to the minus 15 meters and 1.27 times 10 to the minus 17 meters, the black and red lines, will be very unstable indeed. Most of the quantum processed electrons that contribute to giving these very small holons their existence exceed the speed of light, escape the holon, and weaken its boundaries. This makes very small holons very transient entities with very short half-lives. So in keeping with the scheme that we are following, we would expect that the smaller the holon, the more transient its existence. In part 2 of this series, we looked at the concept of interfunction, and we saw how the universal quantum reflexive process inextricably links quantum charges with quantum awareness. And subsequently, we went on to show how structure, life, and consciousness emerge from an ongoing drive for quantum processes to expand and make more space for themselves. So could this transformation of a neutron into a proton, an electron, and an antineutrino be a result of the same driving force? Well, certainly a proton holon at 1.7 times 10 to the 15 meters in diameter is rather bigger than the original neutron holon at 1.6 times 10 to the 15 meters diameter. So having shed some quantum charges, the overall quantum electron speeds will be slower in the proton than the neutron, giving it more stability. The proton holon's constituent quantum charges have more room for themselves. However, the quantum process that goes to make up the electron's charges in the hydrogen atom have enlarged substantially. They have increased the linear amount of space available to them by some 5 orders of magnitude, from 1.6 times 10 to the minus 15 meters to 1.2 times 10 to the minus 10 meters. This ties in with our premise. What about the mysterious antineutrino? In order to maintain an energy balance, some of the quantum processes form an antineutrino. This very small unstable holon, with many of its quantum electrons exceeding the speed of light, rapidly loses all of its own structure. Its quantum processes transfer their extension to the surrounding space holon. Here we are describing a mechanism linking radioactivity to the apparent expansion of the universe. But more of this later. The explanation of neutron decay that we have just looked at highlights a major difference between the quantum process and holon paradigm and the particle and space paradigm. The particle and space paradigm, unsurprisingly, looks at radioactivity in terms of particles. Larger particles are believed to split up into smaller particles, and the smaller particles rearrange themselves in various ways. Vast numbers of collider experiments have been carried out in order to see what neutrons and protons are made of. This has led to the discovery of an amazing zoo of smaller particles. So we have baryons, mesons, quarks, antiquarks, gluons, and many more. The latest fundamental particle, believed in some way to account for all the others, is the Higgs boson. But, as ever, the question that begs an answer is, what is the Higgs boson made of? It is even more difficult in the particle and space paradigm to conceive how this complex zoo of particles relates to the vast regions of space that we see around us. The quantum process and holon paradigm proposes a very different explanation of these processes. It sees radioactivity as a process that builds stable atom holons from smaller, non-stable holons. These new atom holons become the building blocks for holon structure, holon life, and holon levels of awareness that we looked at in the earlier parts of this series. In the next video, 12C, we are going to see how the quantum process and holon view of reality can reduce the number of forces required to explain the universe from 4 in the particle and space paradigm to just 1.